Yes, so everything we will see today is on my GitHub repository here, and you can see the address and go there and check what is there, because there is not only what I'm going to present you, but there is also many other resources like some Colab notebook that you can use for using like powerful diffusion models for generating images from text, from other images, doing in painting, super resolution, and so on. And at the bottom, there are also a lot of other useful resources to find software that you can install, for example, on your computer to generate this model, or some tutorial and guides for how to get better prompt out of it. So if you're interested in it, I suggest you to go here and check out what you like. And there are also two notebooks here. The first is the one that I will present you today. The second instead, it's about a library called Transformer, which is hosted on Hugging Face, and is de facto library that host both Transformer and also diffusion model. So yeah, there's a tutorial about how to use this Transformer, actually diffuser library from Hugging Face. But what we will focus today is how to model the Denoising Diffusion Probabilistic Model, the basic one from scratch, so that you get a little bit an idea of what is behind. So let's get started. So a diffusion model roughly consists of two parts. The first is a predefined diffusion process. This one in green. I don't know if you can see my pointer, but anyway, is this condition, this probability Q that is conditioned on xt-1 and give us x of t. That is the next sample that we get, and it's represented here by this green arrow. Okay, so basically we start from x0, which is our original image, and then we get something that is more and more noisy when we do this forward diffusion process. At the end, we end up with something that is pure noise, x capital T, where capital T is the total number of steps that we are doing in this process. Let's say 200 of these steps, okay? Then we have the process that goes backwards. This is called the reverse denoising diffusion process, and this orange one is a Q of xt given -1 given xt. So we switched the xt -1 and the xt, okay? So basically, here we start from pure noise and isotropic Gaussian noise, and we gradually go back until we recover our image. Okay, so let's break these two processes down in detail, and let's look at what they are doing. So we start from the forward process, the one that transforms an image into pure noise by gradually adding some noise to it. So the formula that we use to generate the next step in the chain is this first one. So x of t is a function of xt-1 multiplied by this coefficient, this square root 1 minus beta t. We will comment in a bit what it is, plus another coefficient, the same actually, beta of t, which multiplies this z of t minus 1. What is z of t minus 1? This is a random variable. Basically, it's just a realization of anisotropic Gaussian here. So a standard normal distribution which is centered in 0 and has covariance 1. So what are these? What is this term beta of t? So this is called basically variance schedule. It's something that we define ourselves and basically tell us how much noise we are adding over time. Okay, so let's say that we have capital T steps, 200, for example. So if we define a schedule like this, we are saying that in the beginning, we add little noise, and then as we go to t, we add more and more, okay? So there are many ways of defining this scheduler. It can be like something a bit exponential like this, something linear, or something even more complicated. For the sake of this tutorial, we will just look at something very simple, so like a linear scheduler. So we are like linearly adding some noise. So we are adding little noise, little by little, at every step we do. Okay, so basically, if we look at this, we can convince ourselves that x of t is actually a random variable that it comes from this normal distribution. A normal distribution which has this mean, the square root multiply xt minus 1, right? And has this variance, okay? So we can just write like this. So this is the standard way of writing a normal distribution, by writing the mean and the standard deviation, okay? Everything fine so far, but then we can use a nice property, which I will explain you in a second. And thanks to the nice property, we can say that x of t is actually a function of x0 plus some extraction from isotropic Gaussian. And the nice thing here is that, first of all, you see, we don't have to condition on xt minus 1. We can just start from x0, which is the first image of the chain. And the second thing is that here in this z, this random variable that we extract, we no longer have a dependency on t. What does it mean? It means that we can compute directly any step here in the chain. We don't have to do sequentially, okay? Because the first equation implies that if t is, I don't know, 180, we have to do 180 of these steps to compute it. Like this, it means no, we just need the starting point, and that's it, okay? And just some variable, this alpha, which we can pre-compute. Okay, so what is this nice property? So this nice property, before explaining it, we define what is alpha t and alpha t bar. So alpha t is just 1 minus beta t, okay? Beta t is this variance, this variable that we define, the way we decide how to add noise in the process. Alpha t bar is just the cumulative product of all the alphas from 1 up to t, okay? So this is what we said. Look at the first line. This is just what we have before, just I rewrote, before I was having beta t, I just rewrote everything in function of alpha, okay? So before I was having 1 minus beta t, now I have alpha t. Here I was having beta of t, now I have 1 minus alpha t, okay? So x of t is, by definition, this one. Okay, good. Now, if we look at this, we see that this is actually a recursive equation because we can express x t minus 1 in the same way. So x t minus 1, now I expanded here in these square brackets. It will be alpha t minus 1, x t minus 2, plus 1 minus alpha of t minus 1, z t minus 2, okay? I just expanded. Now, if I do the multiplication, so I multiply this first term, alpha t, by this, I get this first term. Then I multiply this alpha t by what is inside under the square root, and I obtain this, and this is what was left from before. Now, if we look at these two terms, this one and this one, we see that the two variables, zt minus 2 and zt minus 1, are actually two Gaussians. So what happens if we are summing two Gaussian variables? It's here in the paddings. Basically, if we have one Gaussian variable, z1, which comes from this distribution with center in 0 with this variance, and then we have another Gaussian variable, which is also centered in 0 but has a different variance, we obtain a new variable, which we call z bar, for example, which is still centered in 0, but now the variance is the sum of the previous two variants, okay? So in our case, we have that we are summing this Gaussian variable with variance 1 minus alpha t, and this other Gaussian variable with variance alpha t minus alpha t minus 1, okay? So in the end, we obtain that the new variable has is come from this normal distribution, okay? So we can just use this property and write it down. So here you see I put a bar on top of it, and now I pre-multiply this because this is actually the variance of the new random variable that I have. Okay, now you can think that I can continue this argument over and over because I can keep expanding xt minus 2 and I will have xt minus 3 term and so on. And in the end, I end up with something like this, where remember alpha t bar was this cumulative product, and then I have this z0 bar, which is this final the result of the merging of so many Gaussian variables. And since this is the only random variable that I have, I can as well just call it z. I don't even need index 0 anymore because it will be the only one, okay? So basically, if we go all the way back, we can say that x of t conditioned on x0 is just something which comes from this normal distribution, which is centered in x0 multiplied by this coefficient, which I know how to compute, right? It's just something which, again, I define myself, so I can obtain very easily. And this variance, okay? So this is a nice property. Again, it allows me to drop completely this index t and to avoid doing all this chain for sampling a new element in the chain. Okay, so the thing that we need to do now is to define a scheduler to compute this beta t, because once we have it, we can obtain all our sample just like this in one shot. So the simple thing that we can do, as I said, is to just use a linear scheduler, but more advanced scheduler, of course, can be used, and usually they give a better result. So this is the code. As you see, I just use a linear space. This is the value I start with, and this is the value I end with. Those are just hyperparameters, not so important. The only thing to focus here is that it's a linear. Okay, so then we define the number of time step. This will be our capital T, and yes, it's 200. And then we can compute all the betas using this function that we just defined. Okay. Then this is the code for computing the alphas, so it's just 1 minus betas. And then I also, this is alpha t bar, which is the cumulative product. And then here is just some calculation that we need. So it's the square root of the cumulative product and the square root of 1 minus the cumulative product of the alphas, okay? So this is just, I just rewrote the equation that I showed you before. Okay. So now let's illustrate how noise is added to a sample image at each step of the diffusion process. So let's start from this image. And then the first thing that we do is that we scale the image in this range, -1, 1, and we also convert it to a Pytorch tensor, so we can do some operations. This is just the code. I'm not really commenting it anymore. The only thing to comment maybe is that I also resize the image to be 128 by 128, so it will be a bit smaller. And then here are the other operations that I said before. If I do that and I check the shape of my image, now it's a torch tensor with this shape, okay? So 1, 3 channels because it's RGB, and 128, 128. This is the height and width. Then, since we want also to go back and retransform this tensor back to an image, we also define an inverse function that takes tensor and re-obtain an image. And yeah, this is the image that, this is the result of applying this function. As you see, exactly as before, the only thing is that now the image is a bit smaller because we reduce it to 128 to 128, okay? But yeah, it should be quite straightforward. By the way, if you have any questions, something is not clear, just raise your hand because it's maybe better to answer them right now than at the end. Okay? Yeah, sure. Go ahead. Okay, so now we define the forward diffusion process. We have all the elements that we need for doing it. So the first thing, I'm not going to comment it too much. This extract function is just something to put things in the right shape. You know, if you do deep learning, it's always like a game of shapes, and here it's just a function that puts the right singleton dimension at the right place so we can multiply things properly. So yeah, it's just a utility function. I'm not commenting it too much. What is more interesting instead is this Q sample, which is the actual forward diffusion function. And let's look into it. So you see that we can pass some noise as input, but if the noise is none, so we don't pass anything, we can sample it. And this is basically our Z. And you see that it doesn't depend on T, so we can just extract it like that. We don't have to extract it like many times. I mean, if we are at step 180, we don't have to extract it 179 times. We just extract it once. Perfect. Then we just use this utility function extract before to adjust the shape. So here there is nothing special going on, just I'm putting the square root of the alpha t and the square root of 1 minus alpha t in the right shape. And then I simply compute the sample. You see, I just multiply the square root of alpha t bar by the x0, which is our initial image. So this will be like the center of the Gaussian from where I generate my new sample. And this is the variance, which is this z, this noise, multiplied by the variance that I have at time step t. Okay? So you see that no matter what is the time step t, I can just draw the sample x of t starting from the initial one and from some noise that I extract. Okay, so let's check, for example, what I get of a specific step, t equal 20. So I just call my function, and I get something noisy out of it. Okay, so I have the initial image plus the amount of noise that I have at step 20. And then I revert this image back to visualize it, okay? And this is what I obtain. So this, remember, this is the initial lion with so much amount of noise at step 20. Now I can do the same for more steps. For example, for step 1, you see step 1 there is very little noise. 50, 100, 115, 199. 199 is our capital T. So you see this basically is pure noise at this. I mean, even here, even after 100, certainly after 150, you don't see the lion anymore. You basically see only noise. Okay? And you see that I don't have to do, if you look again at the function which I showed before, the important thing, again, is that we can just compute all these samples like this in one shot without doing all the sequence, all the steps to get there. Okay. All clear so far? Yes. Now let's talk about the backward process. So the backward process is the one that basically starts from something that is pure noise, x capital T, and then gradually goes back until we reobtain our initial image or an image in our initial domain. So if we start from something that is Gaussian noise and is this beta of t is small enough, it means that also the next step, x capital T minus 1, will be something distributed as a Gaussian. So, more formally, it means that this posterior will be Gaussian with some mean that depend on x of t and with some standard deviation that depend on x of t. Okay? So, the problem is that even if we know that all these distributions are Gaussians, we cannot compute this mean and this standard deviation analytically, because this requires knowing the true data distribution. And this should be kind of intuitive because, you know, this, even if this is a sequence of Gaussian distribution, in the end, we have to converge to the distribution of our data. And the distribution of our data is clearly unknown. We don't know that. If we knew that, we don't have to do deep learning. We can just take it and analyze it, sample from it, do whatever we want, okay? So clearly, this distribution, P of x0, is unknown. So this chain, even we know that all the elements in this chain are functions that we know the shape very well. Well, we don't know all this change where it goes. So this means that we cannot express this function mu tilde x of t and sigma tilde x of t analytically. So what do? Well, we use a neural network to learn them. Okay, let's see how to do that. The first thing is that we actually do a simplification. So we don't really let sigma x of t to depend on the sample x of t, but we just say that it's a time-dependent constant, and we call it beta t of tilde, okay? People have also learned this, and it can work a bit better maybe, but makes things a bit more complicated. So now, for the sake of simplicity, we just say that, yeah, this variance is something which is predefined. So the only thing that basically now we need to learn with a neural network will be this first term, the mean, okay? This is something, the variance is predefined. Okay. The second thing that we do is that this is our posterior distribution. We just condition them also on x0. This is something that we can always do. The only point of it is that it helps us to do some manipulation, so algebraic manipulation to get some result or a shape, a form that we can handle better. And in the end, there is some mathematical derivation, which I will briefly show you. Actually, I will not show you, but they're here. We just go to back to them in a second. The thing is that using this sort of transformation, we can obtain that this posterior distribution is actually a normal distribution with this mean and the standard deviation. The mean depends on xt and x0, but for the sake of simplicity, I will just write it like this. So this will be my my mean, mu tilde of t, and this is the standard deviation. Okay, so the equation for the standard deviation and for the mean are this. We will comment them in a second. I just want to say that I will not go through all the derivation here. You can look at them if you want. They are quite simple if you want. The only thing that I'm using here for doing this derivation is the Bayes theorem, some properties of the Gaussian distribution, and then the nice property that we have seen before, okay? So if we do all this derivation, basically, we see how to get from this distribution here to something in this form, where the standard deviation is like this and the mean is like this. Okay, so let's take a look at this standard deviation at this mean. So here, if you look at here, you see that we have all things that we already know. We have the alpha t bar, which are the cumulative products of the alpha. We defined them before, we know them. We have the beta of t, of course, we know them, right? We have the scheduler that defines them. So everything that is red here, we know. It's very easy, it's given. It can be pre-computed. What about the stuff that is blue? Well, also here, most things we know. We have the alpha t that we know. We have the beta of t that we know. The alpha t bar that we know. The only thing that the x of t that, well, we know x of t, right? Because that's basically our starting point. So we know also x of t. The only thing that we don't know is this one. So this is the amount of noise, the noise that was added in the forward process, okay? That we don't know, because now we are going backwards, so we don't know exactly what noise was added at that time in the forward process. So what we do is that we try to approximate this z of t tilde with a neural network. So basically, our neural network is something that takes an input, x of t, and the time t, and spits out x of t minus 1, okay? That is basically x of t minus the amount of noise that was added to x of t minus 1 in the forward process, okay? And this network, it's a pretty simple network. It's basically a denoising autoencoder. I don't know if you know this kind of model, but this is just a neural network that takes some image that is noisy and spits out an image that is clean, is without noise. It's a pretty simple neural network. Okay? Equivalently, we can say that our neural network takes the same input and spits out the amount of noise that was added there. Okay, so what neural network we are going to use? We are going to use a unit. Some of you are familiar with units, and you know some tasks where they are used for. Image segmentation, exactly. So what is particular about image segmentation is that our input and output are things which basically have the same shape, the same height and width. So there is a one-to-one relationship with the pixels, for example, in the input and in the output. Well, even here, right? So this is our input, the image with noise. This is our output, the noise that was added to the image at the previous step in the forward process, okay? So they have exactly the same shape, so that's why it's convenient to use a unit. So this is a, we'll say, rather standard unit with some down block that, this is basically the encoder, this is the decoder part, and you see that everything here, it's rather simple. I made a mistake here. This is actually downsample block. Here is upsample block because when we go down, we reduce the dimensionality, and when we go up, we can go back to the original dimensionality. So this should be like a downsample, not upsample. But beside that, all the other parts here are quite standard stuff, like convolutional block, group normalization, some attention layer, and some residual connection, which are this yellow line. The only thing to notice here is this part over here. So to do this denoising operation, we also need to tell the network at which step we are in the chain. This step is defined by the time index t, okay? It can be like 20, like we saw before, 50, whatever. The problem is that neural networks are not really good in handling this kind of digits. So what we do is that we take our digit, like, I don't know, 10, and we have to transform it in some sort of signal that is more interpretable for the neural network. And those are the positional embeddings. If some of you know transformers, they are basically the same thing. So they basically take some number, like 10, and transform it into a wave like this. So here you have an example of the blue and the orange wave are for time step 10 and 12. So the waves are very similar, almost overlapping. Time t equal 30, it's a bit more shift. But anyway, we compute, let's say we are at time t equal 30. So we compute this green wave, and then we concatenate this green wave in front of every pixel, okay? So we obtain like a sort of block like this. So this is gonna be the actual input to our neural network that knows both the image and the time step that we are in, and then it can predict the amount of noise that was added at time step 29 in this case, okay? So the unit is in the repository. I'm not going to comment it any further. I just load it, then I give it the input image, and then I check out what I get out of it. And yes, it's a vector, a tensor with the same shape of the input. And this is going to be basically my noise, okay? So this is just to see what comes out. I give an image with this shape, 1, 3, 128, 128, and I get another tensor of the same shape that represents noise in this case, okay? Okay, so now let's talk about the loss. So what I want to do, what I want this neural network to do is that this is the amount of noise which I was putting into the image in the forward pass. I want the neural network to recover, to predict, to understand what was the network that what was the amount of noise that I added. So basically, my loss function, it will be just a norm, for example, an L1 norm between this noise and this noise. So this noise is something that we know, basically. It's something that is given us we just during the forward pass. It's just something that we extract randomly. And this noise, instead, is the one that is predicted by the neural network. So we can write this term here as the output of the neural network that take in input x of t, the image, and t, the time step. Again, we can express x of t as this value here under the square root. That is something that we know, right? Is these alphas, we have full control over them. X0, that was our original image. It's something which just comes from our dataset, so we know even that. And that this is another term that we know. And then Z, it's some value that we just extracted, okay? So simply, we can sample Z, compute X of t, and then recover Z with a neural network, okay? So it's something really simple that we do for training. So this is how the actual training process works. So we extract some time index t, and then we extract some noise z. So we compute the noisy image at time t. And then what we do is this process. Okay, so we sample an image from the training data, x0. Then we sample z at randomly. We also sample the time t at randomly, and then we take a gradient based on this loss function. So the loss function between z and the noise predicted by the neural network, which takes an input x of t. Okay? So this is very simple. So you see, maybe this now should kind of answer your question, that we are really have full control about deciding what is the time t. It's just something that we sample. So we sample, like, I don't know, time 38, perfect. So we compute the noisy image at time 38, and then we ask the neural network to recover the amount of noise that was added at step 38. And that's it. Because our neural network, the only things that needs to do is to denoise the image, to kind of produce, understand what is this amount of noise that was added in. Okay, so let's put this into code. So this is the function that takes our unit, the noise model, the x0, x start, time t, and then we also define the loss type. So what we do is that we random sample the noise, z, we compute x of t. Remember, thanks to the nice property, we can compute all the x of t just in one shot by just drawing some noise. And then the predicted noise is just the output of the neural network, the UNet that we saw before, that takes in input the noisy x of t and the time step t. Okay? And then we define the loss. So in the slides, I was showing the L1 norm, but we can also use the L2 norm or the Uber loss, which is basically an L1 norm that just behaves like L2 norm in zero, just because it's better, it's differentiable. But by the way, we can just focus on the first line, and the L1 norm. And you see that the loss is just between the noise, this stuff, which a random sample, and the output of the neural network. And that's it. That's all we need to train the neural network. And I think this is one of the beauty of this model, that it's actually super simple. We just take some noise, compute some noise image, and then ask the neural network to recover that noise that we just sampled. Okay? Do you have any doubts, question about this? All clear? Okay, but training, should be easy. It's, as we say, just denoising with some bells and whistles around it. What about sampling? So now we trained our network, and now we want to actually generate samples. So we want to start from some pure noise, and we want to get our image out of it. Well, the thing is, now we have to do all the steps. We cannot skip them anymore. We have to start from the very beginning, from pure noise, and then we have to gradually denoise everything until we reach our image. So every step here is kind of indicated by this image. So we start, as we say, from isotropic Gaussian noise, so something which is very non-informative. And then at every step, we can modify a little bit this distribution from where we are sampling from. Basically, we shift. We are no longer in zero, but we shift ourselves in something that is called mu tilde t-1, and the equation is this one that we have seen before. And we also are changing a little bit the shape, the variance of this Gaussian distribution we are sampling from. So we start from something that is as large as 1, and then we gradually shrink the variance until at the end we have no more variance, and we just return the center of this of the distribution, and that's going to be our image, this green mu0. Okay, that's our final image. So what we can say about it, that first of all, our process is sequential. So as I said, we said 200 steps, then we have to do 200 sampling. That's why these models are quite slow to generate the image. Okay, they cannot generate them on one step, they have to do all the sequence. The second thing is that this process is stochastic, because every time we are drawing, we are doing actually 200 drawings from a normal distribution. So it means that even if we start from the same initial noise, we might end up with a different image at the end. Okay? Okay, but beside that, we should know all the other terms, all the other things that we need to do this sort of sequential drawing. And this is the sample algorithm. So we start, as I said, by sampling some pure noise. And then for all the capital T steps, what we do is that we sample some from Z if T is greater than 1. Otherwise, we don't do anything, because it means that we reach the end of the chain and we just return our mean, mu0, which is here. And then we generate the next sample. So the next sample is given by this term here that is mu tilde of t. Is this stuff over here? You see, is the center of the next Gaussian. And you see that here we have also the Z, the noise, which is actually the one predicted by the neural network. So is the neural network is slowly removing this kind of noise. And this is this posterior variance that gets smaller and smaller. Okay, so we repeat this process with this posterior variance getting smaller and smaller, and eventually, when we are at the end of the chain, this terms is 0. There is not this anymore, and this will be our final image that we return. Okay, everything clear so far about this denoising procedure or sampling procedure, that we gradually start from something, pure noise, and then we gradually remove the noise with our neural network until we end up with our image, which is noise-free. All good? Yes. Okay, so that's it. So the only thing which is left to do is to put this equation into code. So here I'm not going to comment things too much because this is really just writing down the equation into code. So here I have all the calculation which I need for the posterior. So the square root of 1 over alpha t, and then the cumulative product and the posterior variance. And then here is the function for computing the sample. So the first thing is that we adjust the shape with this utility function extract that we seen in the beginning. Then we use the neural network to predict the noise that used to predict the next mean, so the next center of the Gaussian distribution from where we are sampling from. And then here we just draw the next sample. So if we are at the end of the chain, we just return this model mean. So we're done. We just return the image. Otherwise, we do another sample. Just this is our posterior variance. And this is this random noise that we extract. And our next sample is going to be the model mean, the one that we used, predicted using the neural network, plus this z multiplied by the posterior variance. Okay, so I just put into code the equation that we have seen before. And you see, even here, nothing too complicated. Okay, so this is just some utility function that is applying this function that we have seen, that we have just defined p-sample iteratively for all the t steps. So every time we generate some noise, we draw some sample, and then we concatenate everything in this list of images. And this is just for doing this operation in a batched mode, so like for generating, I don't know, 16 images at a time, for example. So again, nothing really interesting here, just some utility functions. And now we are finally ready to train the neural network because we have everything that we need in place. So what we will use for training this neural network is Fashion MNIST, which is basically a collection of images which have 28 times 28 sides, exactly like the original MNIST. The only difference is that rather than being digit, like in MNIST, they are clothes. So we have, I don't know, skirt, pants, bags, and things like that. Okay, right. So we just import the data set. The image size, we say this 28, like in MNIST. There is only one channel because they are grayscale images. And we will use batch size of 128 because, yeah, the images are quite small. Yes, here it's just some utility function that applies some basic image preprocessing on the fly, random horizontal flips and rescaling in the -1 range. So rescaling in this range, of course, it's necessary when we are passing input to the neural network. We also do some things like random flip just to I don't know, because it helps a bit to prevent overfitting. But again, it's not the key point here. These are just the function. But this is very standard boilerplate code that you basically use all the time when you're training some neural network for computer vision. So I'm not going to comment this too much. Here, I just load again my unit, and I define the optimizer, again, standard stuff, nothing too interesting here. And here is the training step. So you see that what we do is that we take not only one image this time, we take a batch of images. This was like our X0 before, just now we have a batch of X0s. And then what we do is that we sample T uniformly from 0 and capital T. Again, this is something that we have seen already before. And then we compute the loss using the function that we have defined before that takes in input the model, the batch of images, and the time steps. And that's it. We just repeat this for 10 epochs. And then we're done. So this is, I'm not doing the training here online, but it doesn't take much. Like on my laptop, it takes around 10 minutes. So it's It's a short training. So once we are done with training, we can actually generate our samples using the function that we have defined before. So here I'm generating 64 images at a time, and you see that after only 10 epochs of training, we already start to see something out. So we start to see some shoes, something that resemble a t-shirt, a jacket, and so on. So actually, we managed to get something to work. Of course, if we train it more, we take the optimizer, which is a bit more fine-tuned and so on, we can get even better results out of it. But this should convince you that even with this simple function that we defined so far, we are able to get something out of it. Yes. So before going to the next part of the tutorial and taking some questions, again, I just want to tell you what are like the next step that can be done at this point. Well, the most important and interesting thing that we will actually see in the next part of the tutorial is that we would like to condition the image generation using some sort of input, for example, a string. So, for example, we want to say, hey, I don't want any image. I want only images of shoes, for example, right? That's what these models are interesting for. So we will see how to do that. Other comments is that, as we said, we made like a strong simplification by saying that the standard deviation in the backward process is actually not learned, or it does not really depend on the previous sample. And we made a strong simplification saying that, oh, this is just a time-dependent constant that we already know. Of course, if we use something like this and we use a neural network to learn this standard deviation, we can get usually better performance. Another thing is that we used a very simple noise scheduler, just a linear one. And also this is kind of naive. There are much better scheduler which can give you better performance, and both in what you get out of it and in time, so in computational efficiency. And the last thing is that, as I commented before, the process of training it's okay, but what this model sucks for are the sampling part, because you have to do all this chain. You have, for example, in our case, we have to generate a single image, we have to do 200 steps. So we have to denoise, use our neural network to do denoising 200 times. And you can imagine that this not scale well when images are really big. I mean, now we are dealing with toy dataset with images of 28 times 28, but that's not really what we are after. Maybe we would like to generate images which are 512 times 512 or even more, and these things does not scale well. So that's where latent diffusion models come into play. So we are not going to talk about latent diffusion model in this today, but I have, as I said, a notebook which introduced the diffuser library, which basically is the de facto library that also you can use to deploy a latent diffusion model. And the good thing is that these models are very fast and they can run even on your hardware, on your gaming PC, you can run this kind of models, or even on a Google Colab notebook, okay? And you can imagine that this is really good because this basically democratized the use of this diffusion model because it made them available to everybody. And with lower resources, computational resources, it's possible to generate big images, which otherwise would be possible only using some dedicated hardware that very few actors have available. Okay, so before going to the next part of the tutorial, I'm happy to take more questions about what we have said so far. Okay, so what the next part, it's now there's no more coding. It's just about some high-level discussion about how is possible, what one has to do to implement condition generation with something called diffusion guidance. So basically, this means conditioning the generation of our image using something else. It can be like a string, it can be also another image, or whatever you want. Before introducing this concept, I want to give you another perspective different from the one of the Denoising Diffusion Probabilistic Model that we have seen so far. And this is the perspective of the score-based methods. So DDPM, Denoising Diffusion Probabilistic Models, and score-based methods are two things which were kind of developed independently by different people, but it turned out that they are doing exactly the same thing. They're really two different views, two different perspectives of the same thing. So why do I even, if they are equivalent, why do I even bother telling you about this second perspective? Well, first of all, because you are aware of it. And when you read score-based method, you know that they are actually the same thing as the Denoising Diffusion Probabilistic Model. The second thing is that talking about this conditioned generation, it's a bit easier in this second perspective. So we will use this second perspective to introduce this concept. Okay, so in the perspective of the score-based methods, the denoising process corresponds to taking some steps in the direction of the score function, which is the gradient of the logarithm of P of x. So P of x is the distribution of our data, and basically this means that we are taking some steps toward the part of the distribution where this distribution is like steeper, or it's has the higher modes. And during this process, we are adding some noise to avoid getting stacks between some modes or saddle point of this distribution. And this process is called stochastic gradient Langevin dynamics, or short as GLD. So what does it mean? Imagine this is our distribution of all images which have 28 by 28 pixels. And so this is the space of all images 28 by 28. And this is the distribution of our dataset, the Fashion MNIST. Maybe this top peak represent, I don't know, images of bags, this other peak, images of shirts, and so on. So what are we doing is that we are navigating this space, this distribution, and we are kind of going climbing the steepest cliffs, okay? And in this process, we also had some noise because it helped us to get unstuck from some local minima or some mode. Now, of course, this distribution is fake. It doesn't look like that in reality. In reality, it's much more irregular, much more like holes and stuff. So we really need this noise to kind of get out of some holes, we get stuck into it, and manage to reach the highest cliff. Okay, so what, as I said, here maybe this taller cliff represent the images of bags. It's taller and maybe has, it's a bit sharper because maybe there are more images of bags than images of shoes in our data set. And also because images of bag, they are a bit more similar to each other. So maybe this peak, this mode here is a bit sharper. But maybe, I don't know, maybe we want to generate an image of bags, so we don't want to end up here. So that's the question, how do we do that? And here is where conditional models come into play. So what we want to do is that we want to condition the generation of our image X based on some input Y, where Y could be, for example, the string bag, okay? So we want to get an image X of a bag given a string that says bag. So in the score-based perspective, this means following the diffusion means following the diffusion this score function. So this is the score function of this posterior distribution. Okay, so you see that it's the same thing as before. The only thing now that there is this conditioning on y. Okay, so let's look at this equation, which is given by the Bayes rule. So the posterior distribution of x given y is equal to the posterior distribution of y given x times p of x divided by p of y. Okay. Now, if we apply the logarithm, okay, because here we have a logarithm and we take the gradient with respect to x, we get this equation. Okay. So the logarithm means that if we have a product, things get summed up and division turns into subtractions. And then when we apply the gradient, these terms actually goes away because it does not depend on x. So we are left only with these first two terms. Now the screen is cutting the second part, but basically after here I just have these two terms here. Okay, this one goes away. Okay, let's look at these two terms. So this term is the same one that we have before, okay? This is just the unconditioned score-based function. What is this? Well, p of y given x is exactly what an image classifier is trying to fit, right? So this is the probability of having a class string bag given an image of a bag. This is exactly what an image classifier is trying to do, okay? So if we can think of it as an image classifier, and if the image classifier is a neural network, then it's very easy to compute the gradients, right? Because neural networks are differentiable. So this term actually is not so bad. It's quite easy to compute. And this is good because this stuff is what we had from before, is what we were training our generative model to do, and this is just an image classifier. So pretty easy to implement, okay? Some questions so far? All clear? Maybe yes, maybe not. Let's see. Let's move forward. So we can decide to give a different contribution to the unconditioned score function, which is, again, what our generative model is giving us, plus the image classifier. And we weight this contribution with some coefficient gamma, which basically tell us how much we want to use the information of the classifier to guide our generation. And this coefficient gamma is called the guidance scale. So the larger the gamma, the larger is the influence of this conditioning signal. So the more our condition signal, the more our string bag will be affecting, will be important in the generation of the image. So if we undo the gradient, so this nabla operator, and we also undo the logarithm operation, we obtain something like this. So we see that the posterior probability of x given y is proportional to probability of x times probability of y given x. So if with gamma here at the exponent. So when gamma is greater than 1, it means that basically this operation is sharpening the mode of the distribution which are associated to the class that we want to decode, that we want to generate. So this blue distribution is the one we have seen before. It was the distribution of our data. This is the distribution of y given x. Here maybe it means bag. So because this mode here is the one associated to the bag. So if we multiply this blue distribution, this data distribution, with the distribution which is the one produced by our classifier, the effect is that we are like amplifying the mode associated to the class that we want to decode. So it means that when we take our path into this landscape, we will end up now to this cliff. Because remember, this gradient is telling us to climb up to the tallest mountain that we find in this landscape. Okay, so if we amplify this mountain, we will much more likely end up here. And the higher the gamma, the more these things will be amplified. Okay, so at some point it will become so high that there is no other place to go for during this step than on top of this mode here. Okay. What I want to say is that the diffusion model is trained as before, and only at the inference time is conditioned on this pre-trained classifier. Okay, and this is something similar to kind of training a powerful unconditional NLP model and then adapt it downstream to a downstream task with a few shot learning. So the point is that we have these two elements which are kind of independent and trained independently, and then we just put them together at inference time. But now we get to some limitations, which are those that you were kind of suggesting. The first is that a pre-trained classifier cannot deal with noise, because they're just not done for that. They never see noise during the training. But this is a problem because the classifier used for guidance needs to deal with a high amount of noise to produce a useful signal during the sampling process, especially at the beginning, because we have a lot of noise. So this classifier is getting maybe an input, an image that is super noisy, and then maybe it doesn't really know what to do. To deal with this, what you can do is to train a classifier that is specifically made for dealing with noise and for the purpose of guidance, but this defies a little bit this idea of having this reusing something which is already out there, because at this point we just can train a traditional conditional generative model end-to-end. Say we just take something which, takes also the input, the string, for example, and then we train everything from scratch. The second problem is that classifiers often take shortcuts, because most of the information in the input is not taken into account when we predict the class. Think about a classifier that has to distinguish between, I don't know, a dog and a car. It's not really taking into account every pixel of the image. It doesn't really take into account, I don't know, the length of the fur or the length of the nails of the dog. I mean, it's enough to detect some feature to just say, okay, that's a dog, and I'm pretty sure about that, or this is a car. But generative model, if we want to generate an image of a dog, of a car, then we have to take into account all the details. We cannot really take shortcuts. And the fact that classifiers do it means that we can take arbitrary directions in the input space when we are doing this denoising, because maybe at some point the classifier is not really haven't explored so much so far some part of the input space, because it just was not necessary to do for doing the classification. So what can we do about that? Here is what classifier-free guidance, or CFG, comes into play. Okay. And this is the next important thing which I will tell you. So, before we just say that the gradient of the log of p of x given y was equal to the gradient of p of y given x, our classifier, plus log of p of x. That was our score-based function. Okay. Now we can express the conditioning term, this one, as a function of the conditional, something that is here, and the unconditional score function, okay? Both of which our diffusion, our generative model is providing. So basically, we can just bring this on the left and this term here on the right, and we have this. So basically, we have that the classifier is equal to the conditioned generation minus the unconditioned generation, or the conditioned score function, more properly, minus the unconditioned score function. Okay? Then we can substitute this thing back here in the first equation, and then what we obtain is this formula over here. And this is the formula of the classifier-free guidance. So basically, we now express the conditional score function as a combination of the conditional and the unconditional score function itself. Basically, we got rid of the classifier. Okay? We express the classifier just as difference of conditioned and unconditioned generation. So, why this is good? Because, as we said before, generative model take into account all the input space. They are much more thorough. So they can provide, actually, they can work as a much better classifier than the standard one for this purpose. And another thing is that this classifier-free guidance is quite easy to implement. It can be just obtained by removing 10-20% of the time while training the conditioning signal. And this procedure is called conditioning dropout. And again, it's quite simple to do, because in practice, the only thing that we have to do is that we have to reply our y, that is our string that we use for conditioning the generation, just with an empty string, like some percentage of the time. So the resulting model now is able to function both as a conditional model, P of x given y, and as an unconditional model, P of x, depending of whether the conditioning signal is provided or whether we just give this empty string, so our fake empty conditioning signal. And here you can see an example of what can be obtained. So on the left, we have images generated using this string, a stained glass window of pandas eating bamboo, using the previous approach, the one that used the actual classifier. Here on the right, we obtain instead images obtained using the classifier-free guidance. So what would you say about these images? Which one you like the most? the right, I don't know, they just look better. They seem more precise. Here, some of them, they're also a bit, I don't know, a bit deformed. Some of them, like this, too. What are those? I mean, some of them are a bit messed up. But there is another thing that maybe you can notice, that this one are a bit more similar to each other. There is a little less diversity, right? So why classifier-free guidance is better than classifier guidance? So as we said, CFG, classifier-free guidance, replaced the guidance from a third classifier, which is this function over here, which a classifier which is built only using a generative model, okay? So basically, as we said, it's the difference of the conditioned generation function minus the unconditioned generation function, which both of these are given by the generative model itself. As we said, standard classifier take shortcuts because they ignore most of the input, but that's okay, because even if they do that, they still obtain quite competitive results in classification. However, generative model, they cannot take these shortcuts. They are really forced to consider all the parts of the data distribution, because otherwise they are simply not able to generate a proper image, right? They cannot afford to not take into account the length of the nails when they generate a dog. Otherwise, there will be some problem with the image that we get out. And this makes them much more robust when we are taking these steps, with the gradient steps in our denoising process, when we are climbing these hills of this distribution. And another advantage is that now we only have to train a single generative model, And this conditioning dropout is very trivial to implement, right? We can just replace 20% of the time the condition signal with an empty string. So we don't even have the problem of training another classifier, deciding which classifier should we use for, because as you know, there are like tons of them. So here we just have a single model, and that's it. But as we were commenting before, there are some limitations. Yeah, sure. Okay, so one limitation that we were commenting on is that classifier-free guidance improves a lot the adherence of the conditioning signal to the image that we want to obtain, but at the cost of the diversity between images. As we were commenting here, these images, they look a little bit like all the same. And this is a typical trade-off in a generative model. So, again, one thinks that's just a trade-off. And this is a reference which I use for this talk.